The formal definition of an arithmetic series is simply the sum of terms in an arithmetic sequence. So if you have an arithmetic sequence and you just simply add up the terms, you get an arithmetic series. And we use a similar subscript notation for series. We use S to represent sum. S1 would simply be the sum of the first term of the arithmetic series, so it would just be T1. S2 would mean the first two terms of the arithmetic series added together, so T1 plus T2. S3 would be T1 plus T2 plus T3. And these are all called partial sums because we can't really add up all of the terms in an arithmetic sequence because we would just keep on getting bigger and bigger numbers. Now, hopefully by now all of you have seen the number file video on Carl Friedrich Gauss and the little problem that he was given adding up the numbers from 1 to 100. Carl Friedrich Gauss is the one who related this story to his biographer, so who knows exactly what happened. It's quite likely that it did occur. I've heard different variations of it, one that he was 6 years old instead of 9, one that he was given this problem as a punishment for misbehaving instead of the whole class being given the problem. This would have taken place in the 1780s, but we actually do know quite a bit about his early schooling. We know who his teacher was at the time. It was a fellow named J. Büttner, and the teacher's assistant was actually also known. His name was Martin Bartels, and he, in his own right, was quite a famous mathematician and was a tutor for Carl Friedrich Gauss. Now, I want to give you a slightly different way of thinking about that problem that will help you remember how to add up the terms in a series. And it's the way I remember it. I think it's a simpler way of thinking about how to add up the terms in a series. So what Gauss was given was adding up the numbers from 1 to 100. So really he was given the problem of finding S100 of the series 1 plus 2 plus 3 all the way up to 98 plus 99 plus 100. Now, instead of matching up pairs, which leads to a problem when there is an odd number of terms, because then you're going to have one term left over and you've got to figure out the number of pairs, and sometimes it can just get a little bit tricky. So in this method, what we're going to do is we're going to take S100 and we're going to rewrite it, but in the reverse order. So 100 plus 99 plus 98 all the way down to 3 plus 2 plus 1. And now we can match up the terms. The two first terms now add up to 101. The next two, 2 plus 99, add up to 101. And the next 3 plus 98 add up to 101, all the way down the line. So in fact, we have 100 pairs of numbers that each add up to 101. And we know there's 100 because there's one pair for every number in the sequence. So you can see this will work regardless of whether you have an even or an odd number of terms. There's only one slight thing we have to do to make this work, because this isn't really S100. We've doubled it because we've added the sequence to itself. So we have 2 times S100. So to get S100, we just have to divide the thing on the right by 2. And you can see Gauss may well have done it this way, because this is a pretty easy way to calculate it. 101 times 100 is just 10,100, divided by 2 is 5,050. But for our purposes, let's see where those numbers come from. 101 was simply the first term plus the last term. So we've got first plus last. And then we multiply it by 100 because that's how many terms there were. So that's how many pairs there were. So we multiply by the number of terms. And then finally, we divide by 2. And that's how you can calculate Sn for any arithmetic series. And in fact, that's really much closer to the way the formula looks. When you see the formula for Sn, it looks like this. T1, which is really the first term, plus Tn, which is the last term, times n, the number of terms, all over 2. Now, there's another variation of this, which I don't particularly like. I don't think it's all that useful, but you will see it, and just so you don't get confused when you see it, we know from the last section that we can write Tn as T1 plus n minus 1 times the common difference d. So in the formula on the left, we can replace Tn with that T1 plus n minus 1 times d. And so we get T1 plus another T1 plus n minus 1 times d, all times n, all over 2. And then you'll typically see the two T1s combined. And this is the way that formula is written. I don't particularly like this one because it's pretty easy to make a mistake with the brackets, put one number in the wrong place, forget to double the T1, all sorts of things. It's much easier just to remember first plus last times the number of terms divided by 2, which is really this formula, and it's a good formula. So let's use that formula in a couple of examples. Let's say we're given a problem to add up 8 plus 11 plus 14 plus all the way up to some unknown number, but we're told we're looking for S20. In other words, we're trying to find the first 20 terms, the sum of the first 20 terms of this series. And typically this is what's going to happen, because the formula requires you to know three things: the first term, the last term, and the number of terms. So here we have the first term, no problem. We don't have the last term, and we do have the number of terms. So we've got 2 out of 3. So our first step is to find that missing piece of information, which is Tn, in other words, the 20th term of this series. And we've done a problem just like that in the last section. The first thing you have to do is write the general term for this series. In other words, the general term for these numbers as if they were an arithmetic sequence. The common difference is 3, so we can write Tn is equal to 3n, and the 0th term would be 5. So 3n plus 5. Now we can find T20 quite easily. T20 is equal to 3 times 20 plus 5, which is 65. And now we've got everything we need: the first term, the last term, and the number of terms. So S20 is just equal to 8 plus 65 times 20, the number of terms, all over 2. And don't reach for your calculator. See if you can do these things in your head before reaching for your calculator to check. Oftentimes they're quite easy. 8 plus 65 is 73. 20 divided by 2 is 10. And so this is just 730. Let's take a look at another variation of this. Let's say we're asked, what is the sum of the arithmetic series 16 plus 21 plus all the way up to 211? Now, in this one, I've stated that it's an arithmetic series because I haven't really given enough terms for you to verify it. But if you come across a problem in this section, you can pretty much assume that it's an arithmetic series. So, once again, we need three pieces of information: the first term, the last term, and the number of terms. We've got the first term and the last term, but we don't have the number of terms. So that's the first thing we have to find. And again, you've done problems like this in section 1. And once again, the first step is to find the general term of the sequence that forms the terms in this series. So we have Tn. What's the common difference? It's 5, so we can write Tn equals 5n, and the 0th term would be 11. So Tn equals 5n plus 11. And we can then say 211 is generated by this general term for some value of n. So we can replace Tn with 211 to figure out what value of n is going to work here. We can subtract 11 from both sides and divide by 5, and we get 40. So what we really know is that this is T40, and we're looking for the sum of the first 40 terms here. So what we're really looking for is S40. So the first term is 16, the last term is 211, times the number of terms, all over 2. 16 plus 211 is 227. 40 over 2 is 20, so 227 times 20. If you double 227, you get 454, and a 0 on the end, so 4,540. All right, finally, let's do this a little bit more generally. Let's find Sn for 10 plus 14 plus 18. So here we don't know how many terms we're going to be adding up. What we really want to know is a formula so that when we're told find the sum of the first 10 terms, we can just plug 10 into the formula. This is analogous to finding the general term for a specific sequence. So again, what is Sn? Sn is simply t1, which we have, plus tn, which we can figure out, times n over 2. So let's figure out tn. So tn, the common difference here is 4, so it's 4n. The 0th term would be 6, so 4n plus 6. So let's replace the tn with 4n plus 6. And not only that, let's replace t1 with 10. So 10 plus 4n plus 6 times n all over 2. We can simplify this. 4n, 10 plus 6 is 16. We'll divide that by 2 to get 2n plus 8. And then we'll expand this to get 2n squared plus 8n. And when you find these, they're almost always quadratic expressions, meaning they have an n squared in them. Let's just check to see that this actually works. If we have S1, that means the sum of the first 1 terms, which is just 10. Our formula says that that should equal 2 times 1 squared plus 8 times 1. Well, 2 plus 8 is 10, so that works. S2 is the sum of the first 2 terms. 10 plus 14, that's 24. Our formula says 2 times 2 squared plus 8 times 2. So that's 2 times 4, 8, plus 16, which is indeed 24. Let's do one more. S3, 10 plus 14 plus 18 is 42. So that is 2 times 3 squared, according to our formula, plus 8 times 3. So 2 times 3 squared is 2 times 9, or 18, plus 24 is indeed 42. And now you can use this to find the sum of the first any number of terms. If I said find S40, you could just simply plug 40 into the formula and have a very quick way of finding the sum of the first 40 terms of this series.